Hi, I'm Andrea, and today I'll be sharing with you a little bit about our work on learning good feature representations that generalize across multiple different preference rewards. To produce complex behaviors in the world, robots can generate trajectories xi that optimize a pre-specified reward function r. This reward is typically parameterized by a theta, encoding a trade-off between different features phi of the task, things like cup orientation, distance to table, or efficiency. And here this Jaco robot arm only cares about being efficient, but in general, the kinds of rewards that the robot should optimize depend on the kinds of behaviors and preferences that the people that they are assisting want. The reward function that the robot should optimize changes, whether it's because of variations in the task, having different users, or encountering different contexts and environmental settings. However, the representation on top of which the reward is built, the features that are important, are shared. If the robot learns the representation correctly, it can use it to obtain the reward function as the task, user, and context change. So our question in this project was, how can robots learn a good representation that generalizes? Meta and multitask learning methods learn the representation from user input that's meant to teach multiple full rewards, like preference queries. As an example, we could use a simulated interface to show different people pairs of two trajectories and ask them to pick their preferred one. And then you can use their queries to learn their preference rewards r theta I, implicitly learning a shared representation. By contrast, we propose that if learning generalizable representations is the goal, then we should just ask the user for input that is specifically meant to teach the representation itself, rather than asking for input meant to teach the reward and hoping to extract a good representation along the way. Recent works in contrastive learning explicitly focus on learning good visual representations by training from data generated in an unsupervised fashion. So given an anchor image, you can apply data augmentation techniques like random cropping, contrast and brightness manipulations, rotations, and obtain what's called a positive image. And then you can complete this triplet with a completely different image called a negative. So now the representation can be trained with a triplet loss, inducing a representation that makes visually similar anchors and positives map closer in the latent space and further from the negatives. However, here the notion of similarity is purely visual, and it's driven by whatever data augmentation heuristics the designer chose. By contrast, in order to learn the representation that people use, so that we can learn their preferences and objectives, we also use their notion of similarity. So we observe that the notion of similarity can be driven by the human. If two behaviors appear similar to the person, then their feature representation should be similar as well. We introduce trajectory similarity queries, where in a simulated interface, we show people trajectory triplets and ask them which two are more similar to one another in terms of their feature representation. For example, here the person considers the left and right trajectory to be more similar because they both stay close to the table and far from the laptop despite looking visually dissimilar. We can think of the person's answers as selecting an anchor and a positive, but because we don't have an explicit anchor, we can think of them as selecting just two positives, resulting in two triplet queries. Our method for similarity-based implicit representation learning, or SIRL, can be used to train an embedding with a triplet loss like before, by using both positives since we don't have an explicit anchor. Once we train the representation with similarity queries, we can collect preference queries just like before and learn each reward on top of the frozen representation. And each of these rewards can then be optimized to produce behaviors in the world. Now I want to showcase to you how similarity with SIRL is different. So let's look at a simple example in a grid world where the robot navigates from a start to a goal and considers the discretized angle of the mug that it's carrying at that goal. When we look at a random embedding that doesn't consider feature similarity in its representation, the most similar trajectories are simply the ones that are close in the state space, while the least similar are also the farthest in the state space. In contrast, SIRL finds trajectories similar even if they are far in the state space or from different start goal pairs, so long as they are similar in feature space. And the similar trajectories can be similar in state space here. We put SIRL to test in two simulated environments, Grid Robot, a grid world with 4 ground truth features, and Jaco Robot, a replication of our Jaco lab environment in a PyBullet simulator also with 4 features. And in both environments, we had a simulated human answer queries based on these features. We compare SIRL, which is trained with the similarity queries, to 5 baselines. a randomly initialized embedding, which doesn't benefit from human data, but it's also immune from any spurious correlations that could be learned from biased data along the way. A VAE pre-training, which learns the representation in an unsupervised fashion. And an embedding trained with generic preference data from 1, 5, 10, or 50 different human preferences. And we look at two quantitative metrics. First, we wanted to measure whether the embeddings themselves contain the necessary information to recover the foreground truth features in each environment. And prior work actually argues that good representations are linearly separable. So what we did is we froze each trained embedding and took a held-out test set of trajectories labeled with their ground truth feature value phi star, and computed the mean squared error between the predicted feature values with a linear layer on top of the representation and the ground truth feature values. And we call this the feature prediction error. The result is that for both GridRobot and JacoRobot, we find that SIRL in orange results in representations that better predict the ground truth features than any of the other baselines. Next, with our second metric, we test whether good representations necessarily lead to also learning good rewards across the board. So we took the trained embeddings and we performed reward learning with preferences from 20 simulated test users. And we tested the accuracy of the learned rewards by using them to choose amongst trajectories from a held-out test set. So we use these rewards to do preference selection, and that gives us the test preference accuracy. Here I'm showing the results for GridRobot with 3 different amounts of training data increasing from left to right. And we see that SIRL in orange consistently gets better test preference accuracy than any of the other methods. And meanwhile, for the JacoRobot, we also see that SIRL performs better, but it needs a little bit more data to learn a good representation that performs better. We also ran a user study with 10 participants, and we first asked participants to answer 100 similarity queries by looking at 3 trajectories in our interface and picking the 2 most similar ones. So here we show a video of the interface where the participants can rotate the 3D view, switch the predefined views, and click to record their query answer. And then we also asked them for 100 preference queries by picking the more preferred trajectory out of 2. And we used the simulated interface that is quite similar to the Similarity triplets one. And what we found is that with both the feature prediction error and the test preference accuracy, SIRL does better than a random embedding, which was our best performing baseline. Thank you.